Now that we have completed our modeling part almost, like all the geometrical profiles, shape, slope, material properties, sectional property, everything has been assigned. Now we can also define some other inputs like loading. We have also assigned the support conditions. So right now we will just see how we can define different loading inputs. Now, first loading input that we are going to apply here is the wind load. Now, of course, we also have the probability of having the seismic action, but considering that it's a very low-rise building and it's a metal building, structure which is more ductile, so we are in this case ignoring the seismic action, but you can take the seismic if you want to have it considered. But for this model, I'm taking a wind load. Okay, so before we define the wind load, please remember to uh, define the wind definition. Like wind loading is like where we are defining the direction of the wind, how the wind is going to hit the building, and we are defining its directions, like windward side, leeward side, x-axis, z-axis, or different other information, like if you want to scale up with some factor, and so on. But when you are defining the wind loads, you also need to define some basic information like wind intensity. At what intensity the wind is going to be imposed on the building. That is known as the wind intensity or the wind pressure. Now, intensity is also a function of several other parameters like, the location of your structure, the geographical and the topographic information of the site, then the height of the building, sometimes the geometric shape of the building. So these are different parameters as specified by different codes from which you can calculate the wind intensity as a function of its height. Now here we are also going to do the same thing. We are not calculating, means I'm not showing you the exact calculation, how to calculate it, but you can refer to any standard code and check the complete procedure to calculate the wind intensity from the basic inputs. So what we'll do here is we will define the wind intensity values. So let's see how we can define them. So here you can see if you click on this wind definition, you can see like type. I have selected type 1 and you can see like wind 1 and there is a small window pops up. Now, this is a dialog box for the wind definition where you can define the wind intensity in a spreadsheet format in the input table, or else you can also use some cost-based automated process to generate the intensity. Here instead, we only have the AC code, then a SNP code, and also I think the GB code. These codes are implemented for the automated wind intensity calculation. So, but for any other codes like Indian code or Euro code or any other international design codes, you need to calculate them and define it in this table. So let's see how we are defining it. For example, in this case, if you take the AC, then you can see here you have several inputs. You can directly define it. So, for example, in this case, let's take this AC based calculation. If your structure is based on some other location which demands some different inputs and calculation, just go ahead and calculate as per your different formulation and copy that and paste it in this spreadsheet table. Okay, now that we have used our AC calculation procedure to calculate the wind intensity, next is the factor. Factor is nothing but it's like it's an amplification coefficient. Like whether you want to amplify, you want to scale it down, if you want to, reverse the direction. So basically, it's for scaling up and scaling down. So we are keeping the factor as one, but what happens, why we need it? For example, um, if a facade of a building, for example, it's not completely closed, that means there are few portion which are left out for the wind to pass through, or we can say like there is some openings. Then of course the wind can't uh, push at those location because it can pass through. So effectively, the entire area has been reduced. So we can't take the entire area for calculation of total wind load because the wind intensity is not falling on this entire area. So my effective area, which is exposed to the wind load, has been modified, right? So if you think that if any of your face is having some reduction in the area due to some openings or doors or windows or any kind of perforations, then you can just approximately calculate the net area which is exposed to the wind and define it as a factor. For example, 20% of the area is reduced, then you just define it as a zero point 0.8. So here I am taking the full area that has been exposed. Now here, please note that we are not defining any direction. We are just defining like, okay, this type 1 is like assuming that wind is blowing from a left direction. If you follow my cursor from this end to this end, we haven't defined the directions. We are just planning like we will define the wind intensity of certain amount to this direction. So just tag it as a type 1. Later on, we'll define the direction. Right now, we are just giving the inputs for calculation of the wind intensity. Similarly, if you have any other, if you want to define any other type for some orthogonal action, for example, the wind is hitting on the other orthogonal direction, and assuming that this face is not exposed as 100% to the wind load. So basically, its effective area has much reduced. In that case, you can't assume like 100% effective area. You need to reduce the exposed area. So just go ahead in the factor box where you define some reduced value. And also, if the wind intensity, which is based on the building structure, then wind speed, if you think that, okay, this direction, it's different, wind speed and building geometry, other things which are different, then you can have the different inputs. So you can define multiple type 1 and type 2, type 3, and so on. When you are defining the wind load, I will show you in this load case, then you select the respective type and assign the direction. Okay, now before we go ahead, please note that we have a very powerful tool in STAAD. We call it the group. A group is a very powerful feature where you can group several set of members by some specific group name or some panels by some floor group name, some node by some group. They are very much useful. For example, if you want to apply the flow load on some panel, then also group definition is very much essential. If you want to select few of the members, for example, set of trusts, you have tagged them as a group. Then with a single selection by the group name, you can, get them all of them highlighted. So we have different advantages if you group them for hassle-free and much convenient workflow. So next, what we'll do is we have only defined a single wind load definition, type 1. Later on, if we'll see if you want to add one more wind type for the orthogonal directions. But my wind definition is over. Now next is I'm going to define the dead load. Now dead load is simply the gravity load, which is attributed to the member self-aid, and if there is any kind of load which is sitting there forever, then it will be taken as the dead load. Now let's take the dead load because it's a factory shed. Basically, it's most of the dead load is coming from the self-aid and also from the load which is ascribed to the sheeting and all. Okay, now before we define the flow load, sorry, the dead load, please note that here we have not modeled the sheeting, the roof sheeting, the metal sheeting with the plate elements because there is no point. First of all, these metal sheets are very thin. They are very much having very insignificant stiffness compared to the main structural frame. So they don't contribute to significant stiffness. But yes, they have the purpose like they will transfer the loading to those supported purlins, girts, and then the web sections. Sorry, the tapered sections. Okay, now here, as we haven't defined any plate elements for representing the roof sheeting, we have just kept all those panels as open. So, but we have to simulate the loading, right? So what we'll do is we'll apply the flow load here. Okay, so let's see how we can define the flow load. Now, please remember that before I go ahead with the detailed discussion on the flow load, I will create few group for the for defining the floor panel. Why it is required? Well, I'll define the flow load. I will explain it with much more clarity. So before that, let's define the floor panel. So here you can see I have defined the group name as a floor one and selected the type as floor because we are defining this panel particularly for facilitating the flow load application. Okay, so we have created a group name called inclined one, but next we have to assign it to certain set of panels. So we can keep on first defining the name, then we will assign them by selecting the required panels. So we are taking this right hand side slope as the first category for applying the flow load because it is having the same slope. So we are considering this entire coplanar sheet as floor panel type 1 or maybe inclined 1 as we have defined. So we have selected all of them as all of them has the identical slope. Now we will assign them. You can see we have already defined the name and we need to just associate with the selected members. Now these set of this complete panels would be treated as inclined one, which has been named while we have defined the floor group. Similar way, we will take the opposite end and select the respective panels. So this should be closed or else the closed panel won't be identified. Now we will select that as inclined 2. Okay, so we have inclined 1 and inclined 2 for the two opposite slopes of that structure. Okay, now we will apply the loading later on, but before that, there is a very important thing that we have missed out, but we need to assign it. It's called the bracings because it's a steel structure. Most of the steel structure are not resisted laterally by the moment connection. In steel structure, we can't rely entirely on the moment connection. So the lateral movement to resist them, we need to assign some bracing system or the lateral framing system. So there are different attributes and different functions of those braces. We can assign the braces on the vertical frames and also on the horizontal planes. The reason is the building can twist, it can rotate about its plane rather than completely uh, drifting. So that's because the building is not having any kind of diagonal bracings on the horizontal planes. So we can apply some diagonal bracings on those roofs so that building has significant stiffness against the rotational activity. Next, we'll assign the bracings on the vertical frames. So this is just a demonstration. Maybe in the real life model, you will add some different procedure or some different patterns of bracings. So these are for the roof, and similarly, we can go to the opposite end. Now you can see that these extreme ends are braced at the roof so that building can't have some torsional movement. Although there would be certain degree of torsion, but this kind of bracing would stiffen or would rather resist the any kind of significant torsional activity. So generally these are also known as the tension rod or some tension member because they are generally treated as a very slender sections which is not supposed to take the compression just by virtue of its tension it will resist the movement. A similar way we will take the vertical planes of the frame and assign the cross bracings. Okay, now this one looks quite practical if you just imagine a factory shed building. It is having a whole lot of bracings at the top and at its faces. Now I have just defined the location of those members, but I haven't defined any kind of property. So if you go by the missing property, you can see these are highlighted. Now I will get them first highlighted and take them to the new view so that I have the ease in assigning the property to them. So go to the beam tool because these beam members are highlighted. Uh, Geomet Go to specification, prismatic. Now these are generally like solid bar-like sections, circular bar-like sections. So you can give some information of its diameter of those bars because as I mentioned, these are generally treated as some tension rod. So you can see here the material property is by default taken as concrete. Later on, you can change it to steel. Now just checking how it looks like in 3D view. Okay, seems like these members are assigned. Now you can see some thickening of those line members. Okay, this is very important. Just while I have shown this model, I thought of saving them. But all of a sudden, I thought, like, why don't I share this very important information to you? This is like while you are working on this live model, please make sure that the model has been set as auto save so that you don't have the risk of losing the model in case the model get crashed or due to some issue in your machine. You have to close the model, but if it is not saved, then you can't recover the model. So all your hardship would just go in vain. So it is the strong suggestion from us to keep on saving it at frequent interval. Or if you think like manual saving is very risky because someone might forget to frequently save it, then you can make sure that your autosave option is perfectly saved. So you can access this configuration. Go to this startup page, go to configure, go to option. Now you can see here there are some options like save, auto recovery information and all. And also in your model on the top, you can see a small slider called autosave. Please don't forget to switch that on so that in case your machine crashes or your model crashes, you won't lose your model that you have spent a significant amount of time in creating. You can immediately recover them. This is we thought it's important information because we have come across different issues from user like they have panicked, got disappointed, and all of a sudden came to us like, okay, I have spent like 2 or 3 weeks on this modeling and somehow we have lost the model. My computer got crashed, the model got crashed, how to recover? So we can't do anything unless and until you have either manually saved them or you have set the autosave option on. Now here you can see on the top, auto recovery, there is a small slider. Just keep it like on. Okay. Now there is a very important member specification we are going to assign, which is called the tension only. Basically, these cross bracings, these are generally considered as tension only members because they mostly behave to withstand the tension, and once it experiences the compression, they get switched off or got buckled because they are very slender in nature. Basically, they're not meant to handle the compression. So we need to assign some property like, okay, once it experiences compression, it will be switched off because it doesn't contribute to any stiffness. But once those members experience tension, they would be the stiffness of those member would be considered. So we need to assign this property as tension only to those cross bracing, but I'll assign it later on, how to assign it. But before that, let's again go to the loading part. Okay, now this time we are going to, okay, now please remember that here we already had defined the win definition, right? But there is a very a quick way or a very quick trick by which you can define the exact portion where the win load is supposed to be imposed. This is not a feature which is shown in the GUI. You can define it through GUI. There is a way by which you can define it through the input editor. So just to select the plane, just consider this plane where you can specify that, okay, these are the areas where the wind load is going to hit first. Now, for example, I don't want like these bracings are to be considered for experiencing the wind loads. I want that, okay, my external sheeting or the facade is resting on those purlins and those web members. So I want those wind loads to be hitting on those members only. Now instead, the wind loads is basically applied as a nodal load because it is just calculating the total force out of the effective panel area, then the intensity. It is just multiply with that and determine the force, and those force are then further calculated and discretized as nodal load. And depending on the effective tributary area, it will impose the nodal load. But before that, you need to define this influence area, right? Okay, now here we are subdividing into three different groups to define those panels, vertical panels, where the wind load is supposed to hit. Now please remember that don't get confused with the floor load. Floor load is basically for the dead load, gravity load, but here we are defining the wind load. The procedure is different, but there is some similarity. In flow load also you have seen that we have defined some grouping so that we can define the flow load exactly on those grouped panel name. Similar way we can define the vertical panels and also tell that to apply some specific wind load on those panel area only. Okay, so we are subdividing into two different uh, set of panels. Now here you can see I have selected three different frames, but my assumption is like in between these selected frames there is an opening because we are assuming that okay in this factory shed, for example, in this phase there would be some gates or doors and this would be kept as open. So we are not selecting this panel. So just follow how we define the required panels and instruct STAD to specifically identify the zones where the wind load is supposed to hit. This time don't use the selection type from the group as floor group. Please remember this. This is to be selected as a beam. Give a name like wind 1, then wind 2, because this is not basically floor load. In case of floor load, you select the panel type as floor, but here select the panel type as beam. In fact, you won't get this information in the help manual. This is just some internal feature we know. So very powerful feature. In fact, you can use it to apply the wind load to some specific zone. Okay, this portion also we are treating as a different panels where wind load is also supposed to hit. So we have fragmented the panel definition.